How do phasors simplify AC circuit analysis problems? Imagine trying to solve a puzzle where the pieces are constantly moving and changing shape. That's what analyzing alternating current circuits can feel like. But what if there was a way to make this puzzle more manageable? That's where phasors come into play. They are a powerful tool that helps engineers understand and work with AC circuits more easily. In AC circuits, voltages and currents don't stay constant. They oscillate sinusoidally, meaning they follow a wave pattern that repeats over time. These waveforms are described by sine or cosine functions, which include the amplitude, frequency, and phase angle. Analyzing these directly in the time domain involves solving differential equations, which can be complicated and time-consuming. Phasors change this game by turning these time-dependent waveforms into simple complex numbers. Think of a phasor as a rotating arrow or vector in a two-dimensional plane. The length of the arrow shows the amplitude of the wave, and the angle indicates its phase relative to a reference point. By representing sinusoidal voltages and currents as these vectors, engineers can work with them algebraically instead of solving differential equations. This transformation makes calculations much more straightforward. Instead of dealing with changing waveforms, you work with fixed points in the complex plane. When you want to find the current flowing through a resistor or the voltage across a capacitor, you just use algebraic formulas with these complex numbers. Complex impedance combines resistance and reactance into one value, making it easy to see how they affect the circuit. Using phasors also makes applying circuit laws simpler. Ohm's law and Kirchhoff's laws, which are fundamental in circuit analysis, work just as they do in direct current circuits, but with complex numbers. This means you can calculate voltages and currents in AC circuits with familiar algebraic methods. Another advantage is the visual aid of phasor diagrams. These diagrams show the relative sizes and angles of voltages and currents, helping you understand how they interact. Once you solve the circuit in the frequency domain, you can convert the results back into time domain waveforms to see the actual voltages and currents as they vary over time. Phasors are especially useful when analyzing circuits at steady state, where the circuit has settled into a consistent pattern of oscillation. They also make it easier to study how circuits respond to different frequencies, which is important in filter design and signal processing. To sum up, phasors simplify AC circuit analysis by turning complex, time-varying waveforms into manageable algebraic forms. They convert differential equations into simple algebraic equations, allowing for quick and clear calculations. They also let you visualize the relationships between voltages and currents with phasor diagrams. This approach is a cornerstone in electrical engineering, making the analysis of AC circuits faster, easier, and more accurate.